喂，好，大声，可以调小声，很大声，好，一下哦，OK，好，喂，好，哎，这个就yeah, anyway, yeah, so okay. So yeah, so today I'll be presenting this paper by uh, Hoffman and Pignatelli. So it's let me write down the archive number. So it's 2207, the 06845. Okay. Okay, so this paper is about a explicit construction called the simple vibration in one-two surfaces. And yeah, so this is basically uh, just a very concrete example of constructing a variety. So yeah, today's talk will be hopefully very easy to follow. Okay, so before we do the construction, so yeah, which is the main theme of today's talk, let me begin by giving a quick survey of the background of this construction. So in the theory of algebraic surfaces in particular, or more generally, the varieties of general type. So this means that the variety has an ample canonical divisor. And for those kind of varieties, we can actually draw a map. Okay, so first we do this in the two-dimensional case, that is surfaces, or minimal surfaces. So we can draw on this map about the distribution of some invariants of different kind of surfaces. So over here, we have this axis representing the geometric genus PG. So this is the geometric genus. And on the y-axis, we have the volume, which is the self-intersection, top self-intersection of the canonical divisor, this volume. So it is a classical result that if you consider all possible surfaces, then their invariants must lie in this region, bounded by these two lines. So this is the possible region for these invariants to live in. Okay. So in particular, these two are represented by two inequalities, and this one is called the yeah, so, and Miyaoka-Yau inequality, and this one, which is our more important to us today, is the Noether inequality, okay, which reads kx squared must be at least 2pg minus 4. Okay, so this is called the Noether's inequality that dictates that these invariants must lie above this line. So this line is also called the Noether line. Okay, so this is a well-known result for surfaces, and we will naturally ask if there is a similar theory for threefolds. So there indeed is. So we look at projective threefolds. So again, we draw this distribution. On the x-axis, we have the geometric genus, and on the y-axis, we have the volume, x cubed. So again, we have these two types of inequality, one on the top and one at the bottom here. So these are again called the Bogomolov Miao-Ka-Yau inequality and the Noether inequality. Okay, so again, the allowed so all threefolds must have their invariants lie in this region. And in this time, we the form of the Noether inequality is this: kx cubed must be at least 4/3 pg minus 10/3. Okay, so this is the Noether inequality for threefolds. However, this is not precisely true because yeah, so for general threefold, whether this inequality holds is still an open problem. And what is known is that so yeah, this form of Noether inequality is proposed around the 90s, and over the past few decades, we were able to prove them in increasingly general assumptions. So as the current status holds, I think we know that this inequality is true for all Gorenstein projective threefolds. And this is the work done by Professor Chen Rongkai and Chen Meng in the 2015. Yeah. And we are also, there's also progress in dropping this this assumption. So if we drop the Gorenstein assumption, maybe let me use, yeah. Then it is known that there are some exceptions for the BMY inequality. And for the Noether inequality, this holds true except for possibly PG from 5 to 20. So this is still open problem, whether this inequality holds true for the 5 to 10. So it's actually better. So we only know for these 6 values are still unknown. Okay. So yeah, so this result is also by Professor Chen Rongkai and Chen Meng and Zhang Chen in just no more than 5 years ago. It's in 2019. So it's a fairly new result in the development of this theory. Okay, so in the research of these kind of inequalities, there's this variety that reoccurs a lot. So this is also known that, at least Professor Chen told me, that they know for a variety to lie on this Noether line, it must be this following certain form. So X would be not on the Noether line unless it has the following form, unless it is a fibration, or it can be realized as a fibration over P1, whose fibers are degree 10 hypersurfaces in the weighted projective space P1125. Okay. And this surface, so P1125, this is three-dimensional space, and a hypersurface in this space, so this is a two-dimensional thing, it's a surface, and it is called, it is the one in our title, it is called the 1-2 surfaces, 1-2 surface. Because if you do the calculations, it has volume 1 and the geometric genus 2. Okay, so if you plug in to the Noether inequality for surfaces, you see that the left-hand side is 1, right-hand side is 0. So it's quite near the Noether line. It's not on the Noether line, but it's quite near. And also it has a fairly small geometric genus. It's in the smallest possible PG for the right-hand side to be non-negative, right? So this turns out to be, this kind of construction turns out to be important when we want to understand varieties that lie on the Noether line. So the goal today is fairly simple. We're just going to construct this X explicitly in a way such that we can do many explicit computations. So yeah, so this is what we'll be constructing today. So our plan is as follows. So the plan. So the first step, we will construct this F, which is a P1125 bundle over P1. So you can think of it as a total space that contains this X. And the X is a degree 10 hypersurface. In this F. Okay, so it's it cuts down this F. Okay. And this is the X we'll desired here. Okay. So we'll look at this X more carefully. In particular, we'll show that first it is indeed Gorenstein. So it is in the case where we know for sure that this Noether inequality is true. And we'll also give a description of the singular locus of X. Secondly, we will show that X is indeed of general type. So yeah, that's kind of the premises we have to ensure to make sense. Okay, so we'll show that X is of general type. And lastly, we will check that its invariants, in particular the geometric genus and the volume, indeed satisfy the equality on the Noether line. So yeah, so equality in the Noether inequality, and so this X indeed lies on the Noether line. Okay, so yeah, so it's basically just a few checks, and yeah. So after finishing all these, we will slightly mention that there are actually some, how do I put this? So up to now, you may think that this construction is kind of particular, but we will mention a result to show that this kind of construction is actually pretty general. So in particular, we will look at the moduli space of threefolds of general type with some given value of invariance. And we will actually, the punchline is actually that these kind of families that we constructed actually form an open set in the moduli space. So in particular, it is dense on one of the irreducible components. Yeah, so that's kind of nice because, you basically get a lot out of this construction, right? So yeah, so that's our plan today. So yeah, without further ado, let's start the actual construction. Right. Okay. So first, let's describe a P1125 bundle over P1. So the idea is fairly simple. We consider a C6 with coordinates T0, T1, X0, X1, Y, and Z. So we can sort of see what we're doing here. We want this T0, T1 to be the coordinate downstairs for the P1, and the X0, X1, Y, and Z are the coordinates for the weighted projective space P1125. So to make that happen, we let the C star squared act on this. Okay, so the action by lambda and mu sends this to, well, you want downstairs to be P1, so of course there would be a lambda here. And you want upstairs to be fibers to be P1125. So there is mu to the first power, mu square, mu fifth power here. Okay, so in other words, we let the C star, the two scalars, act on this C6 by weights 1, 1 and 1, 1, 2, 5 here. But this is kind of trivial because you're just gluing, you're just doing this separately. So in order to get a more interesting results, we allow these lambda to mix into these x0 and x1. So in particular, the paper uses notation, the weight d minus d0 and d0 minus 2d for these two variables. So in, this means that we have a lambda to the d minus d0 and d0 minus 2d here. Okay. And also, without loss of generality, up to permuting these two variables, we always assume that this one is the larger one. So we assume this weight is larger or equal to, assume this. Okay. Yeah. So if you like, you could just as well call it A and B, but apparently the author made a wise choice here, or calling them d minus d0 and d0 minus 2d. So the algebra later will perhaps get easier to work out. Okay, so after we construct this action, we just define this bundle F to be the quotient. Define F to be the quotient of C6 minus some irrelevant part. So this I is T0, T1 intersect X. It's basically the origin of the affine space and the quotient by this action. Right. So pictorially, what we are doing here is something like this. We have this big space F upstairs, and it projects onto the E1 downstairs, such that every fiber upstairs, so say this point, has this fiber, and this fiber is a weighted projected space P1125. Ooh. Anyway. Sorry. Pause掉下来。Right, so yeah, these fibers are P1125. And keep in mind that this F is actually a fourfold. And of course, this weighted projective space is a three-dimensional thing. But the blackboard is two-dimensional, so this diagram can be deceptive, but just keep in mind that F is a fourfold. So in particular, this definition, from this definition, we can see that F is actually a toric variety. And this toric nature of F makes it easy to actually compute many things. So for example, using the toric description, we can actually compute the class group of F to be Z squared. Okay, and we can actually choose a set of generators, one called H and one called F, where H is defined as the divisor defined by T0 to the power of D0, X0. And the F is defined as the divisor defined by T0. Okay. And yeah, so this class group is actually computable, and you can actually find a very explicit generator of this group. And again, pictorially, this fiber is the divisor defined by actually just the point 0.01, the preimage of the point 0.01. So it's actually a fiber. So F just looks like a fiber. And H it looks like the horizontal thing. So something like that. This is H. Yeah. Okay. And on top of that, we can compute several other things. among these. So for toric varieties, sorry. Yes. So I think, yeah, you just have to make sure that yeah, you could choose other generator other than this divisor, but they will all look like something horizontal. And yeah, the author preferred to use this one, so I'll just follow his choice. Right. So for toric varieties, we actually have this kind of don't want to erase this. Can I use this word? Is there people online? Yeah, but the camera isn't shooting this word. So yeah, anyway, I think I'll just first write it down and see whether I can keep it on the board. So first, we compute these so-called torus invariant divisors, which are simply the divisors defined by vanishing of each coordinate. And these divisors turns out to be crucial in our following computations. So I'll just first write them down. So I'll probably omit the class notation of. So the divisor defined by vanishing of T0 and T1, they are just the fibers, right? Because that's kind of the definition, okay? And so the divisor associated to x0 is h minus d0f. And similarly, x1 gives d0 minus 3d f. And similarly, dy is 2 times h minus df. And dz is 5 times h minus df. Okay. So yeah, these computations are actually not that complicated. So as a demonstration, say if we want to compute the divisor the x1, that is, we want to know, since the class group is generated by h and f, so we just want to know if it's linear equivalent to ah plus bf, what are the coefficients a and b? It turns out, so basically you are trying to say that x1, so this represents the function x1, and this is the divisor associated to the function oh, I got anyway. So it's associated to the function t0 d0 x0 to the power a and t0 to the power b. And basically you're requiring that this the quotient of these two functions is a rational function on the space F. So basically, you're requiring that after the action by lambda and mu, there's something that pops out on the numerator, x0, x1, and also something that pops out in the denumerator. So there's lambda something, mu something, and this thing you started with. So you're trying to let these lambda cancels out and the mu cancels out. So there's two equations for two unknowns. So you can solve it to be that A is 1 and B is d0 minus 3d. So basically, that's how you compute all these, right? Okay, so next, we will compute several other things. Right. So now we have these knowledge of these divisors. We can compute a few other things. So first, the tautological bundle on F is H minus dF. Okay, so yeah, it's basically you're trying to find the degree 0 in lambda and degree 1 in mu. The divisor has a divisor that has those degrees, and it turns out to be this one. So this is a tautological bundle on F. And also we got this canonical divisor on F. And this is also due to the toric description. It is the negative of all, the sum of all torus invariant divisors. So in this case, it's just the sum of all these things, which turns out to be negative 9h plus nd minus 2f. Right. Also, there are some useful intersection numbers among h and f. So because here we are in the fourfold, so the intersection involves 4 divisors, which can be h to the 4th power. This turns out to be f of d, and h cubed times f, which turns out to be 1/10. And anything involving f squared is 0. So let's justify these intersection numbers. So first, f squared is 0 because fibers are disjoint. So this is kind of easy. So because you can move a divisor to its linear equivalent class to compute the intersection number. And it turns out that since fibers are disjoint, so this intersection is null. Now, for the next one, this h cubed f, we look at the quadruple intersection of divisors defined by t naught, x naught, y, and z. So let's think of this. This is an intersection that requires x0, y, and z to be to vanish, and also t0 to be to vanish. So this is actually 1 because it's simply the point x 0, 1, 0, 0 in the weighted projective space, which is the fiber of 0, 1. Okay, so let's call this map pi. Yeah. So this is a smooth point in this weighted projective space, so the intersection is 1. But if you carry out this computation over here, it turns out that this is actually 10 times h cubed f. So this shows that h cubed f is 1 over 10. Right. Good. So the next one is actually quite similar. So you look at the x0, x1, y, and z. This is requiring all 4 coordinates x0, x1, y, z to be 0, but there's no such point in P1125 because the coordinate can't simultaneously be 0, so this intersection is 0. And again, if you carry out this product by these computations here, it turns out to be 10 h to the 4th plus a minus 50d times h cubed f. So you plug in 1/10 to this part, and you obtain that x to the 4th must be half of d. So these are some nice computations that you can do if you have this toric description. So these will all turn out to be useful later. So that's why I don't want to erase them. But yeah. Okay. Yeah. So before we move on to, so up to now we constructed this P1125 bundle over P1. But what we really want is a hypersurface in F, which is of degree 10, and when it intersects with each fiber, it intersects a 1,2 surface. So before we do that, let us look at the singularity of this F. Okay, so maybe let's draw on this diagram again. So what is the singular locus of this F? Well, you can, since F is basically a fibration with each fiber being a weighted projective space, you just look at where these weighted projective space are possibly singular. And for the weighted projective space P1125, there are 2 points that are singular, which let's say, let's draw them like this. So one of them is the point 0, 0, 1, 0. Okay, this is a singularity of type 1/2, 1, 1, 1. Yeah, so is this big enough for you guys to read? It's a bit cluttered. Let's write it somewhere else. So this is a type 1/2, 1, 1, 1 singularity. And this is because for weighted projective spaces, the 0 stratum has singularity type. That is, you move the non-zero number to the denominator and keep the remainings, but mod this number. So it's 1/2, 1, 1, 5, but 5 is 1 mod 2. So this is type 1, 1, 1. And similarly, there's this point 0, 0, 1, 0, which has singularity type 1/5, 1, 1, 2. Okay, so yeah, these are the two singular points that you will see on every fiber of this bundle. So you can sort of connect these singular points, so something like this. And we'll call this one S2, this one S5. So in terms of these divisors, we are looking at S2 as the vanishing locus of x0, x1, and z. So this is the intersection of x0, x1, and z. Similarly, sorry, I wrote something stupid. This is 0, 1. Yeah, so S5 is defined to be D0, the x1, and y, the intersection of those. Right, so these two curves inside F is the singular locus of F. And this information will be helpful when we try to put a hypersurface in F. Okay. So one more thing before we move on is that because the singularity types are 1/2 and 1/5, this tells us that you need 10 times kx for it to be packed here. So this means that not x, sorry, f to be packed here. So in particular, f is a Q-Gorenstein variety because Gorenstein means that kf is Cartier, and Q-Gorenstein means that after a suitable multiple, it is Cartier. Yeah, so also, yeah, this is sort of one of the reasons why we want a degree 10 hypersurface. So this 10 emerges here. And also, 10 times h is also Cartier. So also Cartier. That's the last thing I want to mention before we move on. Okay, so now we are ready to really look at a degree 10 hypersurface in this bundle. So this is the second step in our construction. So we define following: a general element x in the linear system defined by 10 times h minus df. Okay, so we can see this x is a degree 10 hypersurface in F. And the reason why we chose h minus df, or I should say, yeah, the reason for h minus df here is because this is simply the O1 on F. So this is actually O10, right? So X in this thing is a degree 10 hypersurface. And we require that it has, at worst, canonical singularity. Then this element is called a Gorenstein. Regular simple fibration. in 1-2 surfaces. Okay. So yeah, maybe we should briefly explain why this why it deserved this name. So first, it is a fibration in 1-2 surfaces because, as we just said in the introduction, basically what you're thinking is that X is a degree 10 hypersurface in this F. This is your X. And when it intersects with a fiber, which is a P1125, it cut out a 1-2 surface. So let me draw this in red, perhaps. Yeah. So this is a 1-2 surface, which means it has volume 1 and geometric genus 2. Okay, so this is explaining the fibration in 1-2 surface part. It is Gorenstein, as we'll see shortly, that X is actually Gorenstein. And the word regular is not in the sense of non-singular. It is in the sense of that its irregularity, Q1 and Q2, are 0. So yeah, X is singular. There are singularities on X, but we call it a regular variety because its irregularities are 0. So that confused me for the first time reading the article. So yeah, so this is why X deserved this name. I actually don't know why it's called simple, but yeah, that's just a name. Okay, so as claimed in our introduction, we will I erased our plan, but maybe I'll reproduce it here. So first, we already done constructing F, and secondly, now we define what this X is. So we have several things to check. The first one, we have to show that X is Gorenstein. Secondly, we have to show that X is of general type. Thirdly, we have to show that its invariants are indeed what we want. So in fact, we will have, yeah, let's maybe just write kx cubed is equal to 4/3 pg minus 10/3. So yeah, for the remainder of this talk, we will mainly focus on checking these 3 things. So first, X is Gorenstein. Okay, to show that X is Gorenstein, what we do is to show that X, a general enough X, can avoid the singular locus of F, that is S0 and S5. So we will show that for general enough X, we can make it not intersect S2 and S5. Okay. So in particular, because X does not meet the singularity of F, it is as a divisor Cartier in F. So by the adjunction formula, Kx is the restriction of Kf plus X. A second. Restrict to X. So let's see. I'm trying to do. I want to say that it's Cartier by saying that. Sorry. Yes. And the line bundle restricted to X is still a line bundle, so Kx is Cartier. But I'm not quite sure because we have to. Kf is only Q Cartier. Its 10th multiple is Cartier, but it's not itself. So yeah, so notice about that. Yeah, but yeah, so I maybe have to call the general fact that hypersurfaces in Gorenstein variety are still Gorenstein. Yeah, I'm not sure if this argument works because is F Gorenstein? No, because yeah. Yes. So since X is Cartier in F, but what I want to show is that the canonical divisor of X is. Yeah, so yeah, ideally it's because X avoids all the singularities of F. So those parts where you need multiples of Kf to make it Cartier are not present in X, but yeah, but that's just the idea. I'm not sure how to make it a rigorous argument. Yeah, but I think it's a general fact that the hypersurfaces in Gorenstein variety are again Gorenstein. Yeah, so yeah, I think the main point is that we can actually make X avoid all those singularities of F, right? So yeah, that's what we're going to do now. Yeah, so I'm about to do it now. So This is actually fairly straightforward to prove the claim, or I should say, very concrete, because what you do is you just look at the equation that defines x, which looks like something like a polynomial. So we can sort it in terms of powers of x0, x1, and yz. So let's call their powers a0, a1, a2, and a5. So here we treat the t0, t1 part as a coefficient, and we sum over all those kind of variety, those kind of possibilities. And but this polynomial must define a function that is linearly equivalent to this divisor, 10h plus 10 times h minus df. So in particular, if you look at the h part, you will need the a0 times 1 plus a1 plus times 1 plus a2 times 2, and a5 times 5 should be should add up to 10. So that's the requirement. I'm going to write down here. This adds up to 10. Okay. And if you look at the f part, then this gives you the restriction on degree of this coefficient. So this c must be a homogeneous polynomial of degree negative a0 of degree negative a0 d minus d0 minus a1 d0 minus 2d. It's basically just compare the degree, the coefficients here and there. But then you could do some reductions of this polynomial. For example, first, C000 and C005, that is the terms, the monomial in Z and the monomial in Y, their coefficients must be constant. Because of yeah, you just plug in 000 and 005. You see this is 0, this is 0, so this has degree 0, which is a constant. And this constant cannot be 0, because if it's 0, then we would have the entire S2 or the entire S5 be contained, or else S2 is contained in X, or S5 is contained in X, and which will make X has worse than canonical singularities. Okay, so the singularity is not even isolated. So yeah, so this gives a contradiction. So after rescaling, you could rescaling y and z, you could assume that 000 and 005, these coefficients are both 1. And secondly, since A5 can only be 0, 1, or 2 because they have to add up to 10, and these are non-negative. So now we have one term that is 0, 0, 5, 0, 0. Yeah, so 0, 0, 0 is the term where A5 equal to 2. There might be terms that involves A5 equal to 1, but you can do a completing of square, the 配方法. You could complete squares to eliminate those terms that contains to cancel linear terms in X terms. Sorry, in Z. So that there is only a Z squared term and no other linear terms in Z. Okay. So after you do all of these, gotta hurry. We get actually I can just write it here. Maybe just here. This equation becomes a bit fuzzy. So you have one term in Z squared and one term in y to the 5th power, and then some remaining ones. So since there will not be Z terms anymore, the restriction becomes A1, A0, A1 plus 2A2 is 0. And since we single out the one monomial only containing y, there would not be a A2 equal to 5 term in the remainder. So it's the remaining stuff. A2. So putting X into this form, you can see that we have the points 0, 0, 1, 0 cannot be in X because there will be a 1 here. And similarly, 0, 0, 0, 1 cannot be in X because we have Z squared term. And that's great because this means that the points on S2 and S5 cannot lie in our hyperplane X, which is our claim that we want to show. Yeah, so this proves the claim. So great. Now we know that X is indeed Gorenstein. And actually, if you further analyze these equations, and by that I mean you do a case-by-case study to sort of, you consider based on the values of D and D0 in your construction, you can determine which terms can or cannot appear in this equation. And on the other hand, you have the understanding of singularities based on their local equations. So For example, those are studied in Reed's YPG or say Kolar-Morley's book that we seminared last semester. By those understanding of singularities and which terms can appear in this equation, you can actually give a fairly explicit description of what singularities actually appear on this X. So the proposition is the following. So first is a singular locus of a general X. Also, we write X with parentheses d0 to indicate which values of d and z0 we use in the construction. So the singularity of a general element that we constructed is contained in S0, which by this naming, you probably can guess its definition. It's the intersection of dx1, dy, and dz. So all singularities of X lie in this curve. Moreover, X is non-singular if and only if d0 is in the range of d to 2/3 of d, or d0 is equal to 7/8 d. And it has this many terminal singularities, 8d0 minus 7d terminal singularities, if and only if d0 is in the range 7/8d to d. And it has canonical singularity along S0 if and only if d0 is in the range from 1/4d and this value. So looking at this proposition, the first thing you will notice is that this inequality is always true because we, in the first step of our construction, we demand that the weight of lambda acting on x0 is greater than x1. So if this is not the case, then you just swap the roles of d0 and d. And secondly, you should notice that d0 must be greater than 1/4 of d in order to have no worse than canonical singularity. So this kind of family is only interesting to us, or at least satisfy our definition that it has Edwards canonical singularity, only happens when the d0 is at least d/4. So you can actually draw a little something like this. So this is the range of d0 when it's between d/4 and 7/8d. When d0 is in this range, it's canonical. It has canonical singularities. And if d0 is exactly 7/8d, or it's between d and 2/3 of D, then it's non-singular. And finally, if it's in the remaining this part, then it has terminal singularity. So this is the description of singularity on X based on the values of D and D0. And all of this is done because you have this explicit equation over here that you can analyze. But anyway, the important point is that X is Gorenstein. So yeah, so yeah, if you're happy, you can just stop here. But yeah, you could characterize it more explicitly. So let's move on to the, sorry. Yes, it's actually, let me check the paper. It's actually the terminal singularity whose, it's a CDV singularity whose equation is, local equation looks like Tx1 plus z squared plus y5. Yeah, so locally, those singularity look like this. Yeah. Yes, this is CA1. Sure. Okay, so next thing we have, we want to show that X is of general type. That is to say, the canonical divisor of X is ample. And I mean, do I need this? I need this. Let me erase here. So second step, show that it's general type. So this is we want to show that X, Kx, which is by a junction formula, this thing. And you see Kf is that guy over there, and X is in this guy. So you add them together, you get H minus 2F, right? H minus 2F restricted to X. Okay, we want to show that this is ample. And it turns out that for toric varieties, we actually have a criterion for ampleness that pretty much resembles the Kleinman criterion for ampleness. So let's denote this AH plus BF, this divisor, to be D. Then D is ample if and only if A is greater than, A is positive, and B is greater than negative A times minimum of D and D0. And it is NEF if these equality holds. Okay. And the proof is that, sorry, it should be here, that we have a criterion that is quite like the Kleinman criterion. That is, since our X is a toric variety, D is ample if and only if its intersection with all torus invariant curves are positive. An irreducible curve. Right. And all those torus invariant irreducible curve are actually produced by the triple intersection of these D over here. So, for example, if you look at the intersection of D with the T0, Y, and Z, this intersection gives you A, right? Because you have AH plus BF. This intersect with one of F, and then times this. So you have 10 times of H cubed times F, because you have one factor that involves only F. So it's 10 times H cubed F, which is 1, times this A. So it's A. So this has to be positive. So, this is positive if and only if, sorry. Yeah. What I want to say is that the condition of this being positive is what appears in the right-hand side of our lemma, right? So you can do similar things to the intersection of x1, D, and Z. This is B plus AD0, and x0, x1, xy. This is 1/5 of B plus AD. Okay, so these two conditions together gives the condition that B has to be at least A times D or D0. Right. So yeah, that's the lemma. And with this lemma, we can actually say a few more words about the ampleness of Kx. So yeah, Kx is ample if and only if the minimum of D and D0 is at least 3. And it's nef if and only if it's at least 2. Okay. So right. Yeah, so I should write nef and big here, right? So yeah, so it turns out that we have to require this minimum condition to guarantee the ampleness of Kx. So this direction is easier because we just apply that criterion with A equals 1 and B equal to -2. Right, just apply lemma to H minus 2F, and you get the result. Conversely, if either d is less or equal to 2, or d naught is less or equal to 2, we will show that kx is not ample. And we do this by explicitly find a curve gamma that intersects kx with 0 intersection. So this gamma is x intersect d x0 intersect. So it's basically the intersection of d0 and d1 on x. Yeah. And if you do the computation using these numbers, you find that this intersection is d minus 2, which shows that there is a torus invariant irreducible curve such that the intersection is not positive. So in turn, kx is not ample. And similarly, if d0 is less than 2, then you look at kx intersect with s0. This turns out to be d0 minus 2, which is also non-positive if we are we have d0 less than 2. So in order for x to be of general type, this is the condition we want to impose. Okay. Right. Yes. We also call it general type. Yeah. I think there's like not a consistent choice of some author call general type is ample, and some call it if it's big. Oh, it's big, so it's not. Okay. Okay, so yeah, so it turns out we just need 2, right? Sorry. Okay, so that might be some fake memory. I read something somewhere. Right. Okay, so that finished our discussion about X being general type. So yes, yeah, I'll try to do this quickly. But the computation of the invariants are actually not that difficult. So thirdly, invariance X. So we basically, you just have to compute 2 things. One is the geometric genus PG, and one is the volume. Okay, so maybe we start from the easy one. So the volume is basically, since you already know that kx is this thing, so this volume is simply x intersect with this cubed in F. And but x is just 10 times h minus df, h minus 2f cubed. And well, this is simple computation using these intersection numbers. So it's great. You can just carry out those computations to see this equal to 4d minus 6. Great, so 1 done. Only 1 left. The geometric genus is the more complicated one. So we want to compute PG, which is defined as the dimension, it's just a little h0 of x, kx. Right. And to compute this, we consider the short exact sequence 0, kf, kf plus x, kx. This is a restriction, and 0. Okay, so firstly, h0 of this kf is 0 because kf is what? It's very negative. So I think it's like O negative 9 on each fiber. So this has no global section. And actually, we have the vanishing of its H1 as well. So I'll explain this later, but since we have this vanishing, we actually have the equality of this H0 and this H0. So the dimension of this one is just the dimension of this one. And the dimension of this one is easier to compute because you are basically looking at global polynomial functions in variables t, x, and y, z, which are polynomial functions on F that has the class kf plus x, and kf plus x is h minus 2f. So we just juggle a bit with those degrees. You could see that this contains all the monomials in T0, T1 with some degree with one x0. Okay, so you can only have x0 or x1, and you must have one of them because you want one edge. So only they have a single, they have the coefficient before edge being 1, and not y and z because their coefficients are 2 and 5, and also not merely T0 and T1 because they only have f. So basically you have monomials in these kind of forms. And it turns out if you compute the degrees for this kind of monomial, alpha plus beta should be d0 minus 2, and alpha plus beta in this case should be 3d minus d0 minus 2. And in the first case, you have d0 minus 2 plus 1 choices. That's combinatorics. So you have this many monomials, and this many plus 1 monomials of this form. This turns out to be d0 and d0 cancels, minus 1 plus 1 plus 1. Sorry. oh, you just compute the degrees. So, for example, this would have alpha times f, alpha plus beta times f, and plus h minus d0f. And you require this to be h minus 2f. So you compare the coefficients of f, and you get this equation. Similarly, this equation. So when you add them up, this gives you 3d minus 2. This is 3d minus 2. And if you put that into the Noethern inequality, you'll find that this is precisely the 4/3, 3d minus 2 minus 10/3. This is precisely 4d minus 6, which is precisely the volume. Yeah, so kind of anticlimactic, but this finishes our, well, not yet, because I have to show that vanishing there. But this way, we've shown that the Noethern inequality, or rather equality, is satisfied by our variety x here. Right. So how do I show this vanishing? Well, this is where you have to use the Leray spectral sequence. So I need that. Yeah, maybe not. I can finally erase this. So using the Leray spectral sequence, which tells you that this spectral sequence, HP P1. So if this one KF, this converges to H E plus Q F KF, where this small f is this map from F to P1, right? So now we are interested in P plus Q equal to 1. So the H1 of this KF is none other than the sum of PQ equals 1, 0, and 0, 1. So it's the H0 of PM plus H1 R0, which is just this, right? And now you look at those sheaves over here. By definition, the higher direct image is the sheavification of this assignment for U to the cohomology H1 of AF. U, right? So what we are actually trying to do is to show that these sheaves are actually 0, both 0. So of course their H0 and H1 are vanishing. So to say that these two sheaves are 0, it suffices to see this stalkwise. So we look at H stockwise, this is H1 of fiber, KF restrict to fiber. And that one is H0 of this guy. But then AF restrict to the fiber is just P1125. And you can see that KF is this thing over here. So it's actually O negative 9 in P1125. Which, if you know the cohomology of those weighted projective spaces, the ON has vanishing cohomology, except for H0 and the top one. So H1 vanishes on each fiber. And H0 also vanishes because this is negative, so it does not have global sections. Yeah, so this becomes just a computation of cohomology on weighted projective spaces, which are the fibers. And this shows that these two higher direct limit sheaves are both zero, both vanishes. So these two dimensions are also both zero, so everything vanishes, and we are happy. So this, this completes the verification of this invariant geometric genus and its volume, and the fact that they lie on the Noether line together. So, so it's over time. Let me just spend one more 3 minutes to mention this result regarding the moduli spaces. And this will tell you something about why this construction is actually quite important. So this is a proposition. If we consider M, this might not be the standard notation, but I'll just write it this way. MD is the moduli space of canonical threefolds of general type. With those invariants, these invariants, 3D minus 2, okay, is 4D minus 6. Then, so in particular, this says that these threefolds are on the Noether line. First, the family defined by X, and the Gauss, the floor of 2D over 2 is open in MD. Okay, so in particular, it is a dense subset on a reducible component of this moduli space. Secondly, if D0 is large enough, in particular larger, none less than D, then every X constructed by D0 is in the closure of this family. Let's call this dagger. So dagger. Okay, so this shows that actually, at least in one irreducible component of the moduli space, this example is fairly general. By this, we mean the family of those is a dense subset in that component. Moreover, every such construction can be deformed to one another because they all lie in the closure of the same dense subset. So you can deform one such X to another one. Okay, so yeah, so that's one thing I want to mention finally to sort of stress this the importance of this seemingly very specific example. Yeah, so I think that's all I have to talk about today. But there's actually still plenty of content in this paper, and in fact, we aren't even halfway through this paper after this construction. So yeah, if you find this topic interesting, I think I will keep on reading this paper so we can maybe read this paper together. Yeah. Yeah, but for today, I think that's all I've got. Yeah, thank you for listening. Yes. Yes. Well, I think it's just for the convenience of discussion, because if the inequality goes the other way around, you can just swap the roles of x0 and x1. Yeah. Yeah. That's, yeah. It is, I think it's only for convenience. Right. Um, the case where D0 is smaller than D. I recall it's actually not often the case because yes. Yes. Right. So yeah, in the one diagram I draw, yeah, if D0 is greater than is at least D, then yeah, so I think this proposition only take care of the non-singular cases. Yeah, yeah. So yeah, this equality tells you that X is non-singular. So if X actually have some singularity, then I'm not sure. Yeah. Yes. It's tangent. It's normal bundle. Yes. Yeah, but if it's singular, then the the cohomology may have different behavior. Yes, the special case. Yeah.那个是有好像，但是